I'm going to draw this out as if you have no idea about action potentials at all. I'm hoping that you kind of understand action potentials a little bit in the first place. First bit of knowledge you need to have is that the sodium-potassium ATPase is in every cell of the body. Every cell has sodium, I shouldn't say millions of sodium-potassium ATPases. What these are is, if this is a cell, so I'm going to draw this lots of times in this class. If this is a cell, then you have millions of these channels on the outside. They pump 3 sodium out and 2 potassium in. So potassium is going in, sodium is going out. So that's, every cell has a sodium-potassium ATPase. Every cell uses this to do things like get glucose into the cell and things like that. But some cells are called excital, and they use this to actually change voltage. In order to do that, though, first you need to recognize that there's 2 consequences of the sodium-potassium ATPase, or 3 depending on how you break it down. The first consequence is that there's an ion distribution. Specifically, sodium is going to end up on the outside of the cell. So if you're pumping sodium out, sodium is going to end up on the outside of the cell. Not completely, but for the most part. Potassium is going to end up on the inside. And again, not completely, because there will still be some potassium on the outside. But for the most part, potassium's on the inside. So that's what I mean by ion distribution. Sodium ends up on the outside, potassium ends up on the inside. I have to do a little pause to point out that there is one other ion that we care about. It's actually calcium. Calcium is pumped out based on the sodium-potassium gradient. But at this point, we just need to know that calcium is in this picture too. And calcium is on the outside of the cell. Technically what happens is sodium is allowed in if calcium is kicked out. And so it's tied back to the sodium-potassium ATPase. The other thing that the sodium-potassium ATPase sets up is a charge distribution. And I'll be honest, it's a little more complex than this, and it involves potassium leaking out of the cell more than sodium leaking in. But we can keep it simple and say, if you're pumping 3 sodiums out and only 2 potassiums back in, then you're pushing positive charges out of the cell. So the outside of the cell becomes positive. Again, this is kind of a simplified explanation, but it's close enough for our purposes. So the outside of the cell is positive. And that's the same thing as saying the inside of the cell is negative. The first guy who did this said, let's talk about the inside of the cell. So he said, I'm going to talk about the inside of the cell being negative. So what this is called is the voltage of the membrane which is abbreviated VM, generally equals minus 70 millivolts. Come over here and say, this is a heart, and I know I have very poor artistic skills. This is a heart. There's really 2 different types of cells in the heart. There's kind of the electrical system, which would be the SA node, the AV node, And those muscle cells that are better at conducting electricity than they're necessarily conducting. There's no nerves in your heart, but there's certain muscles that conduct electricity better, and these are called autorythmic cells. Or they're shortened to AR cells. And the way we're going to draw this is we're going to pretend, since cardiac cells are kind of rectangular, I mean they're branched, but just to simplify, we're going to draw them as rectangles, and this is an AR cell. Everything else, all the other cells in here, we're going to represent by this rectangle, and these are just simply called cardiac muscle. What this is called, we'll abbreviate them as CM cells. Where we're going with this is what an action potential is. It's when you change the voltage of a cell over time. So every cell sits at around minus 60 or minus 70, but certain cells can change that voltage and use it to signal things because electricity is very, very fast. In this case, it's going to signal for the heart muscle to contract. I'm just going to draw this right now just as where we're going, and I would either use dashed lines because we're going to color them in with color, or just draw kind of lightly. What an action potential is when we change Vm over time. So we set up this voltage of the membrane, and we're going to change it. And you'll see the change, or the action potential, is different in AR cells and cardiac muscle cells. The action potential in an AR cell looks kind of like this shape. And the action potential, cardiac muscle, looks like this shape. We'll throw in some voltages. Technically, cardiac muscle, the AR cell sits at minus 60 millivolts. Another key voltage, right there, is minus 40 millivolts, and that's 0. Cardiac muscle, some key voltages are, cardiac muscle sits a little bit more negative at minus 70 millivolts. A key voltage is minus 55, and then plus 30. So where we're going with these action potentials is they're going to change voltage over time. This one is going to set heartbeat now, heartbeat now, heartbeat now. The role of this one is to let calcium in to cause muscle contraction. And the reason we're going into this detail is because you can alter these with your diets, or they certainly are certainly altered with pharmaceuticals. So you can alter the shape of this and change heart rates. You can alter the shape of this one and affect heart strength. So that's why we're doing this. And in order to explain how you get this voltage change, we have to talk about voltage-dependent channels and what the specific voltage-dependent channels are. So one was over there. Let's do two. I think we can squeeze it in right here. Is what are voltage-dependent, or sometimes they're called voltage-gated channels. If this is a cell, I'm going to draw my, obviously this is not to scale. What a channel is, a voltage-gated channel is, it's an opening where ions can go through. So they could move, these ions could move into and out of this cell. What voltage-dependent channels have are they have a gate that keeps the gate closed, that keeps the channel closed. And they also have these positive charges. Obviously simplifying a little bit, but they have these positive charges. And those positive charges are attracted to the negative voltage inside of the cell. So this gate It's going to stay down in this channel because these positive charges are attracted to the negative charge inside of the cell. Which doesn't make any sense until you draw the opposite, which is, what if I let that voltage be not quite so negative, if it raised a little bit? And we're talking up to minus 55 in the case of a sodium channel, or up to 0 or plus 30 in the case of other channels like calcium and potassium. What happens then is that little gate says, I'm not as attracted to the inside of the cell now because it's not as negative inside that cell. So this channel now becomes open, whereas this channel was closed. So ions can flow. So the key at that point is just recognizing that certain channels can open when they get to a certain voltage. The third part of that then is, what are the specific channels? And we're going to kind of list them out in table form. Now, I just went through this whole thing about voltage-dependent channels, and I'm going to mess it up, because the first channel I write on the board is technically not a voltage-dependent channel. And I'm going to write this really small. I'm going to write this as a sodium leak channel. So we'll do name here. We'll do when it opens. We'll do ion affected. And the effect on VM. Sodium leak channel is a very small channel that's open all the time in autorythmic cells. And so, continuously or always, just do continuously. So this channel is always open. It lets sodium in, which I will try to abbreviate as short as I can. It's going to let sodium leak into this cell. Since sodium is on the outside of the cell and it's moving into the cell, it's going to raise the voltage on the inside of the cell. So this is going to raise VM. So if we come back over here and we realize that an action potential is changing voltage over time, letting sodium in is a way to get your voltage to go up. So this will raise, increase, make it more positive. We'll just use an arrow. Next one, drawing this one bigger. This one's called a fast calcium. Bless you. And this one opens at minus 40 millivolts. Causes calcium to enter the cell. And since calcium is a positively charged ion on the outside of the cell, if we open up a channel and let calcium flow, it's going to go into the cell. It's going to take its positive charge in with it, so it's going to raise VM. The next one is, again, I just use this symbol for it's a voltage-gated channel, but this one is the AR potassium channel. So the potassium channel is in the AR cell, or autorythmic cell. It opens at 0 millivolts. It's going to let potassium out. This one's always the tricky one, because if you have a positive potassium on the inside of the cell and it leaves, then it basically is making the outside of the cell more positive, which is the same as saying the inside of the cell is more negative. So when potassium leaves, it lowers VM. So not to belabor the point, but it's better to be bored than confused. So if you want to change voltage, generally the way you change voltage is you open up a sodium channel or a calcium channel to get voltage to go up, and then you open up a potassium channel to get it to go back down. These three channels are in the autorythmic cell. I say these three channels, there are actually subtypes of these, so there's more than just these three. But I think it's okay to generalize these as they are. So if we wanted to, we could just say, let's come over here and say, in this cell, again, I'm trying to represent a cell here, is there are sodium leak channels. There's the fast calcium. And there's also the AR potassium. I think before we start making all that, hopefully makes sense. Come back over here and finish this though, because we have three more channels still. We have a voltage dependent sodium. And the only reason I'm writing voltage dependent here is to make sure that we differentiate it from this leak channel. This guy opens at minus 55. Lets sodium in. And again, when sodium is allowed into a cell, it's going to take its positive charge and raise Vm. So this will raise Vm. By raise, specifically, I mean it's going to increase the voltage, make it more positive. Have what's called a slow calcium. And you'll see why when we start drawing this out, because it opens and it stays open for a long time. And by long time, I mean longer than the fast calcium channel. This one generally opens at plus 30 millivolts. I'm not as concerned that you memorize that this channel opens at plus 30. You just know that it's going to open when voltage gets positive. This lets calcium in. And just over here, when calcium comes in, calcium's a positive ion flowing into the cell. This is going to raise Vm. Our last channel then is the cardiac muscle potassium. And again, if you look this up on Wikipedia, you're going to see that there's actually multiple subtypes of potassium channels that we're grouping here. But in general, these open at plus 30 millivolts, let potassium out, and they lower Vm. And these three channels are in cardiac muscle. So we come back over here and say, let's write these in. Say I have voltage dependent sodium, which I'm trying to abbreviate V dependent. I have the slow calcium. And I have the cardiac muscle potassium channel. So hopefully you're kind of getting that there's going to be a sequence of events here. That if this is a cell where sodium starts to leak in, that sodium is going to start raising the voltage. So here, an AR cell is sitting at minus 60, and sodium starts to leak in, it's going to raise the voltage a little bit because a positive sodium is leaking in. It's going to raise the voltage until a calcium channel gets to minus 40. Because at minus 40, the calcium channel says, that's when I open, that's when I should open. So a bunch of calcium starts going into the cell, and it raises our voltage even faster. You get to 0 millivolts, and the potassium channel says, now it's my turn to open because of these gates. And potassium rushes out of the cell. And it decreases our voltage back to our rest, which is minus 60. This sodium leak is on all the time, so when the potassium and the calcium channels are closed, it dominates again. Sodium leaks in, raises our voltage a little bit. We get up to minus 40. Calcium channel opens. A bunch of calcium comes in, raises our voltage even higher. Until we get to 0. At 0, potassium channels open. Potassium leaves and our voltage goes way down. So if we were to write this out, we would say sodium enters through the channel and raises Vm. Again, by raises, I mean makes it more positive. When Vm reaches minus 40 millivolts, fast calcium channels open, and calcium enters. This raises Vm further. At 0 millivolts, potassium channel opens, potassium exits cell and returns Vm to rest, which is minus 60 millivolts. And then if we added a fourth step, the fourth step would be start over. So if we were lining up this number to what's happening here, this is step 1. This is step 2. This is step 3. And this is step 4. Start all over. Now the two reasons I think you should want to know about this is calculate how many times your heart has beat in your lifetime, and it's going to be in the billions. This is happening right now inside of you without fail, and hopefully will continue without fail for another 100 billion beats, or however many billion beats. I guess I haven't done the math lately. So many, many, many billion beats. The other reason is just so I can get it on the video, is you can manipulate this. So it's Wednesday. So Wednesday is Hennager's old man softball nights. So I get to go play old man softball. Back when I was playing baseball, I used to love to chew on sunflower seeds. But sunflower seeds have a lot of salt in them. And so if we were, again, I'm going to erase this. It doesn't necessarily belong right here. I would draw it over there, but if I do it here, I can get it on the iPad. As if this is my normal heart rate without sunflower seeds. I eat a bunch of sunflower seeds. Let's do it this way. Let's say this is normal too. Most of my sodium, I have a normal amount of sodium on the outside. My potassium's on the inside. But now I like my sunflower seeds, and so I eat additional sodium. If we look, just focus on the black, sodium is leaking in at a certain rate right here. But if we add additional sodium, then I will leak in faster. The sodium will leak in faster. Which means I will get to minus 40 faster to kick off those calcium channels. Now the rate of rise of the calcium channel is not going to change. This is parallel. because I'm not affecting calcium, I'm only affecting sodium. And the fall here, going back down, repolarizing isn't going to change because we're only talking about sodium. But once we're back down here, I will leak in faster than I normally would. So sodium, increased sodium, can cause an increase in heart rate. Now, to be honest, it's not going to have too much of an effect because I'm soon going to get thirsty and drink water. Then I'm going to have extra blood in me, so it's going to raise my blood pressure. So sodium is kind of a double whammy because if you don't drink extra water, you just stay thirsty. The concentration of sodium will raise your heart rates. You will generally drink water quickly after having an increase in sodium, but now you have extra blood, and so it's going to raise your blood pressure. So the point of this is we can manipulate these either in our diet, or you certainly can manipulate these with drugs. And that's one of the questions that will be on the test. So the next part then is how does this all work over here in cardiac muscle? And it's similar, but it's different. The first thing that you might ask is that voltage-dependent sodium channel. It opens at minus 55 millivolts, but we're sitting at minus 70. Our rest is minus 70. So how do I get from minus 70 up to minus 55 so I can open this channel? The way it works is some of this sodium that's coming in and leaking in is going to leak across from one cell to the next through that intercalated disc. So this here is called an intercalated disc, which really just means there are gap junctions or holes between these cells. So when sodium leaks in here, it can leak over to the next cell. And in fact, that's how this cardiac muscle is going to stimulate the next cardiac muscle and the next cardiac muscle, is there will be gap junctions in there that will let ions flow from one cell to the next. Calcium is also involved in this. So calcium that leaks in can come across. It's kind of like when you did it in ATP1 and you had these voltage-dependent sodium channels hanging out in the axon hillock waiting to get to minus 55. And the way they got there is calcium and sodium came down from the dendrites and raised the voltage in the axon hillock to minus 55. Here, sodium and calcium come over from the neighboring cell and get this cell from minus 70 up to minus 55. When it does that, there is a whole lot of sodium channels waiting to open. It's just kind of like, again, in the action potential in the neuron, there's a lot of voltage-dependent sodium channels that open all at once. So there's a pretty rapid voltage change. When you get to plus 30, both of these channels open. Both of these channels open at plus 30, and so the calcium channel is open, and the potassium channel is open. I can't really see what that means by drawing lines like that. So what I'm going to try and show you is, if this is, again, this is a cell. During this plateau phase, it's called the plateau phase, calcium is coming into the cell as potassium leaves. So they're balancing each other out. In fact, they're linked. Every time a calcium comes in, the inside is more positive, so then a potassium says it's too positive in here, and so I want to leave. It's kind of like if you wanted to keep the level of water in your bathtub the same, you could have that happen by matching how much water is coming into the tub and how much water is leaving the tub through the drain. So essentially, because calcium is coming in and bringing two positive charges, and every time those two positive charges come in, two potassiums leave, there's no change in voltage. So if we're looking at voltage here, the voltage stays the same for a long, long time. You may be asking, well, why would you want the voltage to stay the same? We're talking about action potentials here, and we want to change voltage over time, don't we? But ultimately, what we want to do here is this calcium entry is causing muscle contraction. So we're at this plateau, so we have a nice entry of calcium, and that's stimulating muscle contraction. Not to go back to ATP1, calcium binds to troponin, pulls tropomyosin out of the way, then actin and myosin can interact through the sliding filament model. Eventually the calcium channels close, so if we now draw an arrow right here, what happens now is the calcium channel closes, but the potassium channel remains open for a little bit longer than the calcium channel. So now potassium leaves and returns our voltage back down to rest. So the first step is sodium and calcium leak from neighboring cell and raise VM from -70 to -55. Now the reason I use neighboring cell, again, is it's not always the AR cell that stimulates the next cell. It could be this muscle cell stimulating the next muscle cell too. At -55, V dependence, sodium channels open, Na enters and raises VM. At 0 millivolts, plus 30, both slow calcium and potassium open. Calcium enters and potassium exits, while VM plateaus, stays the same. I don't know if this color coding helps. Might put a little subtext there that calcium causes muscle contraction. Fourth step, calcium closes, potassium remains open, potassium exits, and VM returns to rest. And the fifth step would be wait till there's a leak over again. Wait until sodium, calcium leak over again. So step one is this leaking over. Step two is here. Step three is the plateau. Step four, there. Step five. So this is the kind of thing where if you sit down with it, you realize, well, I kind of get this. I kind of get this part. And then here again is where you want to look at things for 15 minutes and then let your brain just kind of digest it for a while. So get this part and then rest. Get this part, rest. Just kind of accept that these are the channels that are there and they're going to work together to change voltage over time like this. and then spend some time either listening to the YouTube, or hopefully this will work, so this will go up as well. And at some point it will come together, and it's like, oh, that makes perfect sense. And the reason you want it to make sense is because you will need to understand this action potential and this action potential, because you will need to come up with a drug, a cardiac drug, that affects heart rates. And how that's going to do it is it's going to affect either the sodium channel, this calcium channel, or this potassium channel. If you're looking up drugs and you see that it's affecting heart rates, it must affect one of those channels. And so I would like you to describe the effect of that drug on that channel. If you see that a drug affects contractility, then you know it has to affect one of these calcium channels, potassium channels, or to be honest, there's some that affect sodium, but that's a dangerous channel to mess with because it happens so fast. So usually you'll have calcium channel blockers, or atenolol will affect that. And that's what I'd like to describe for you next, is how beta blockers work.